Testing, testing. Hey, Ujwal, how are you, my friend? Switch over to this. Yes. Hey, my friend Ujwal, how you doing, my dude? You doing good? Good. How's your how's the next I'm doing good, my friend. I'm doing really good. How's the next track coming along? Mazdy, my friend, how you dude? How you doing, my friend? How you doing, dude? It's up? Oh, I'm gonna listen to that. Ooh. Gotta listen to that over the weekend, for sure. Your first release as a duo? Excellent, man. Excellent. You alright? I was working through homework, you're a little stuck. Alright. So you got, do I got Spotify? Check. Let's lower that down here. Do I have Spotify? I don't have Spotify. It's not on SoundCloud? I could get Spotify, though. I might have it on my phone. I don't remember if I have it on my phone or not. I've put stuff on my phone before, but I've probably forgotten all about it. Because, you know, smart things are not what I do. Oh, it's on SoundCloud. Okay. Okay. Like, send me an email, Ujwal. Send me an email, Ujwal, about your about where I can get the link for that. I'd like to listen to it when this weekend when I have the chance. Cool. Master, you said you were stuck, my dude? On some homework there? Four 4.2. Sure. No? Okay. So far, so good. Let's look at C. Interpret the slope. Select the correct choice and blah, blah, blah. All right. So for a median income of $0, the percent of adults. Okay, so that makes no sense. Letter A is not it. For every percent increase in adults having at least a bachelor's degree, the median income increases by. Now, this is the correct one here. Because we want to interpret the slope. So it should increase by $750 on average. The slope here is $750 according to my problem here. So I should pick letter B. I believe there's a radio button here. Keep forgetting I gotta. Okay. Is there a radio button there? Sure, we'll just click on it. Okay. Hey, camera, good evening to you. Good evening. All right, and then we have to explain why it does not make sense to interpret the y-intercept. So the reason why this doesn't make any sense. Hey, Try Hard French Toast, how are you doing, my friend? I'm doing wonderful. I'm doing wonderful. It's been a while. I hope you're doing good. So letter D says, explain why does it not make sense to interpret the y-intercept. The reason is because that would reflect 0% of 0% of 25 years or older with at least a bachelor's degree, which doesn't make any sense. It's outside the scope of the model. So letter C here would be your winner here. It doesn't make sense to interpret the y-intercept because an x value is outside the scope of the model. We actually don't reflect anything below 20% here, according to our model. Nah, that's all good, buddy. I just hope you're doing okay. We check our answer here, and we got it. And there we go. We got our one thing right there. Any questions, Mazdy? Cool. Excellent. No problem. Okay. Fair enough. No problemo. Put my face back on here. Alright, I'm back. I am back. What am I doing today? Today? What are we doing? Oh, we're doing that. Okay. Hey, Susan. How are you doing today? How are we doing today? I hope we've been chill. Wait, I shouldn't have shaved my beard? Why? What's wrong with shaving my beard? I don't see a problem. Wait, my beard looks fine. I mean, it'll grow back eventually, like it always does. I always look younger, but hey, this is what it is. Finished eating? Yeah, I just finished eating myself. Yeah, you know. Everybody says I look super young without the beard, so there you go. Oh, careful about that. I do have some automatic moderation on, so just careful not to spam too much here. Thank you, I appreciate that. Natty, hello. How you doing, Natty? I hope you're doing well. Hope we're doing okay here today. What did I have for dinner? My stonks. Stonks were okay today. I think I made. I'm on the road to recover here, but I think I made back, what, $250 today? So, yeah, 250 today. 250 today I made back. I'm still down quite a bit, but slowly but surely making our way back. $250, I ain't gonna complain. Should have bought that Tesla dip. There's no telling if Tesla dips again if the shorts have their way. It just depends. If the shorts have their way, then depends how far tech will go down. Tesla's one of those stocks that you don't know which way that's gonna go right now. We're kind of at a crossroads at the moment. We have a possible recovering economy, but at the same time, everybody says, "Oh, there's a due for a big market correction because we're in the middle of a bubble." So it's like, well, which way is it, guys? Is it going to be like, are we going to recover because we have post-inflationary dollars after spending a whole ton of money through this COVID crisis, or do we actually have a bubble that needs to be burst? I don't know which one, but yeah, I guess we'll have to wait and see on that one. As much as I love Tesla. Ooh, nice. All right, we'll wait for a few other people here to join the chat. That's fine. Yeah, you pump in too much money, that's just gonna invariably happen. Yeah, that could be a potential problem if the supply side from overseas, if you're importing stuff, happens to cost a whole lot more, and your purchasing power has been degraded because you're printing money. Yeah, then that's a very big problem. Because I mean, like we mentioned here before, again, if we talk about money, $20 is not the same as $20. In fact, when people look at $20, people think of $20 as all. Everybody always uses money as a comparison tool about what you can buy with that money. So it's always like, what can I get if I barter $20 for goods and services? Is my purchasing power strong or is it pretty weak? So that's how people as consumers look at money. And again, I think obviously in the United States it's very uneven about what your purchasing power is from state to state. So some people will receive benefits and some people won't. So because of purchasing power. So if you give everybody $1,400, well, $1,400 in California nets you nothing, but $1,400 out in Montana may net you a whole lot more. So because you can get more with that $1,400, for example. So it just depends on where and and how you spend your money there. But hopefully this whole situation, this whole coronavirus stuff goes away. Yeah, it is more of a complex problem than people are willing to let on. There is a significant gap in wages, like there's no question about that. You haven't raised minimum wage in, nearly 14 years. So, yes, you've destroyed the purchasing power of a lot of people's income, and a lot of people have to have like two incomes to basically, maintain their lifestyle. It's very, very difficult. So that definitely has to happen from 725 to something better than 725. But yeah, you have to be careful about how far you're willing to push it as well. So In some areas, $15 an hour makes a perfect amount of sense. In other areas, $15 an hour is going to be outrageous. So, you got to be really careful about how you thread that needle. Again, a one size fits all doesn't necessarily work. So, I get the idea, but the idea may not be realistically implementable. Um, yeah, but the thing is that cost of living is varied also person to person, right? Because everybody has a different lifestyle that they like to live, camera. So if you have to look at it that way, that's another variable to keep in mind. If you live a particular lifestyle, you spend a certain amount of money per month because that's the way you feel comfortable about how you want to live. I don't know what that is. If it means you have to go buy glass tigers every month, then you go buy glass tigers every month. All right, that means that maybe those glass tigers are rather expensive, then it means you have a higher, lifestyle than maybe somebody who just wants to go out and eat every night, or somebody who cooks every night, or somebody who's just getting by check to check. So, yeah, every person is different about what their lifestyle choices are and how much it will cost to maintain those lifestyle choices. So, cost of living there is kind of a big thing. There's so much more I could say on the issue, to be perfectly honest. Um, it's a very delicate balance, that's for sure. It's tricky, yeah, it's tricky. You have to try and make it work for a lot of different types of people, and then that's very, very hard. Okay, okay, we're getting overtime here. Oh my gosh. All right, let's do this. Okay, let's get started today. Welcome back. Welcome back to Wednesday, end of the week time today. So today, we are moving on here in chapter 5. We're going to finish off 2 other sections here. Oh, camera, I thought you followed me before. Okay, now you follow me again. Hey! um, so, yeah, so as I was saying here, yeah, we're going to finish up sections 5.3 and 5.4 here today, okay? Continuing to move forward here in chapter 5. Remember that, oh, it's a different count, fair enough. So remember here that the test is going to be due on Sunday, all right, at 11:59. So be sure to finish the test and the homework associated with chapters 1 to 4. All right, so that is all they're waiting for you due on Sunday. Okay, this Sunday. Be sure to finish it by then. All right. So today, let's go ahead and continue moving forward here, talking more about probabilities. We talked about the basics of probabilities last time on Monday. All right, we also take a look at, again, we took a look at disjoint events. We took at non-disjoint events. We talked about the addition rule. We talked about the rules of complements. All right. So today we're going to continue where we left off there in section 5.2, and this is going to be pretty relevant for what we're going to be doing here in section 5.3 and beyond. Okay. So let's take a good look here at the big board. Camera. Alrighty. And so what we have here today is here today is we're talking about some objectives here for each one of these particular sections. So let's talk about each one here. So in section 5.3, we're going to talk about independent events. We're going to use the multiplication rule here for independent events. We will compute at least probabilities, all right, as well. And the last part here, the at least probabilities, pardon me, is going to talk about the word at least and what that means in order for us to calculate out probabilities. Okay, remember, in probabilities, wording is especially important here. So this is the first time we're going to stress on this. Well, we stressed on it quite a bit on Monday, to be honest. But we're going to stress on this even more for this particular part. Okay, so the first 2 questions here deal with sections 5.3, and then the last few stuff here. This is a confusing section. Okay, we're going to go over this slow here, Ujwal, and we're going to have to make this understandable, okay? I promise you that. If you already got to look ahead, well, you'll see exactly how this works. Let's take a look at question 1. Question 1 says, what are independent events? All right. So, definition of an independent event. Independent events are two or more events, A and B, in which the probability of event A does not affect the probability of event B. We could also call independent events disjoint events. So we did talk about this on Monday. We said, okay, event A is over here, event B is over here. And if they're independent, then there's nothing that they have in common, okay? They don't interfere with each other, they don't overlap anywhere. All right, one doesn't affect the other. Okay, fine. Two completely separate and independent events. So that leads us to question 2. It says, what is the multiplication rule for independent events? So we're going to make the assumption here, if A and B are independent events, then the probability of A and B, so again, let's note the language here, the probability of A and B, all right, is equal to the probability of A times the probability of B. Okay, so that's what we have here. Probability of A and B. Remember last time on Monday we talked about the probability of A or B. Okay, so in this case here it is A and B. All right, so the distinct difference between the two. If we have two or more independent events, okay, so such as we have event A1 all the way out to AN, then the probability of A1 and A2 and all the way out to AN is just the multiplication of all those probabilities put together. Okay, seems fair. All right. You're probably saying, hold up, hold up, hold up. All right. Now I agree, Ujwal. This is confusing. Now, where exactly does this fit into play here with some of the examples that we're going to look at? So let's do. So majority of this section here is doing some examples here. So because we want actual practical. We want to put this together practically. So let's take a good look here at some particular problems. Okay. All right, so I'm going to bust out the paint tool for this other half. That guy. Okay. All right. So let's take a look at number 12. Okay, so that'll be our first example here. Be number 12. All right. So let's look at number 12 here. It says, what is the probability of obtaining 4 ones in a row when rolling a fair 6-sided die? Interpret the probability. Okay. So let's think about it this way. Okay. And let's get some simple yeses or nos in the chat here. Okay. So if I asked you, is our 2 rolls, let's say I rolled a 6-sided die twice, okay? Are the 2 rolls of rolling a fair 6-sided die, are they independent? Yes or no? So let's at least ask that. Are those 2 things independent? Yes or no? Okay. All right. That's correct. So the answer is definitely yes, right? No, it's not. So think about it this way. Let's think about it this way. If I roll the die, it comes up with a number. It comes up with a number. That's okay. So think about it this way. So I want you to kind of think in this perspective here. I roll the die. It comes up with a number 1 through 6. Doesn't matter what that number is. But my question really comes down to is that first roll affected the probability of the second roll? That's the question. It's like, okay, it comes up with a number. It could be 3. Does rolling a 3 the first time affect the probability on rolling the die the second time? And the answer is no. They are 2 separate things, so they would be independent. You see what I'm saying there? Like does that make sense about why it's no? Okay. Uh, uh, about why it's they are separate independent events. So they are definitely, yes, they are independent. Okay. I just want to point that out, be like, oh, where did that come from? Oh, it came from there. Change it up. Yeah. All right. So with that idea in mind, let's look at each one as their own independent unique event. And then we want to find the probability of each of those independent unique events. So what I like to do here is, let's talk about one of the keys here, okay? Um, the key here, probably what will be helpful the most in this section to reduce the amount of confusion, is just to, at some point, I'm going to, is to just basically draw a picture, just a simple one, draw a picture of each event. Okay, and what do I mean by draw a picture of each event? Well, in this case, I have 4 rolls of the die. Okay, so I'm just going to call, for example, here, I'm going to have 1, 2, 3, 4. Each one's is a roll of the die, so this is roll number 1. This is roll number 2. This is roll number 3. And this is roll number 4. Okay, each of them are separate. Okay. So let's look at roll number 1. All right, and I'm looking at the question here. Remember, it's the probability of, again, rolling 4 ones, okay, in a row. So let's look at roll number 1. I rolled the die. It came up as a 1. Okay. Well, what are my odds of getting a 1 on the die, the first roll? I rolled it. It rolled a 1. What is my probability of getting a 1? Yeah, right? I agree with that. There's a 1 out of 6 chance of rolling a 1 on the die, okay? Right? I rolled the die. There's a 1 out of 6 chance. Fine. Fair enough. Okay. Roll number 2 comes along. Roll it. And it comes up with the 1 again. And I like, oh, just my luck. It's another 1. Okay. Well, what's the probability of me rolling a 1 a second time? What's that probability again? Again, there's separate independent rolls. Okay. Yes, this is true, but let's not put the 2 rolls together. Just for this individual roll. Yeah, yeah, but you're correct. It is 1 out of 36, but for this separate individual roll, I have a 1 out of 6 chance again, correct? Now I look for the third roll. I roll a 1 again. I said I'm having really terrible luck. And again, that would be a 1 out of 6 chance to roll a 1 on the third roll. And once again, on the fourth roll, I rolled another 1. Well, then I have a 1 out of 6 chance there as well. So I have the same chance of rolling 1 each time I roll the die. And then all I have to do is that because these are 4 independent events, I'm just going to go ahead and multiply all these together. And then we're going to see what we get. So let's take a good look here at this thing. All right, so here we're going to do 1/6 to the 4th power here. Okay, reminder to yourself here, by the way, this is not 1/6 times 4. This is 1/6 to the 4th power. Okay. So let's go ahead and put this in the calculator here. Get 1/6 to the 4th power. Go ahead and hit enter. Okay. So hopefully this is what you got here so far. Talk about this here in just a second, but okay. Now let's take a look at this answer here. This is 1/6 to the 4th power. So what is the answer to this necessarily? So sometimes what may come up in the book, at least certain problems, is that you may get answers that look like this, okay, where it's, again, 1 over 6 to the 4th power is really, really small, okay? So the way you want to read this out here is you're just going to take 7, this will be 7.716, okay? Now that blocky letter E here in this case, if you recall here, blocky letter E represents 10 to some power here, 10 to the x power. All right. So basically what this represents is this is 7.716 times 10 to the negative 4th power. So remember, to the negative 4th power means you move the decimal point over 4 places to the left. So if you were to actually write this as a decimal here, this would be 127,716. Okay. So this is how we would write it out if we were to write it out as a full decimal. Okay. Hey Zan, how are you doing? From Argentina? Well, welcome. Bienvenido. All right, I can help you out after I'm done here today, or during my break actually, which will be in about half an hour or so. I'll be more than happy to try and help you. Absolutely. All right. Any questions about that? Okay. So far, so good. That's easy, right? Is that point? Yeah, that's 0.07%. That's correct. No. No. All right. Okay, let's do another problem here then. Okay. Let's do number 15. All right. I'm going to take it up slightly a bit upper notch. Okay. Okay. All right, so let's look at false positives. The ELISA test is a test to determine whether the HIV antibody is present. The test is 99.5% effective, which means that the test will come back negative if the HIV antibody is not present 99.5% of the time. The probability of a test coming back positive, the antibody is not present, or a false positive, is 0.005. Okay, suppose that the ELISA test is given to 5 randomly selected people who do not have the HIV antibody. Okay, so what we need to look at here, we need to be very specific about these type of questions. So you need to be very careful about this. Most probabilities that we're going to run into are going to have 2 sides to it. Okay, so meaning to say, on one side of the equation, this test here that we do to detect whatever, all right, is 99.95% negative, all right? So what we have here is we have 0.995 is going to be negative. However, on the other side of the coin, what happens on the opposite side? What happens if we get a positive? Well, that's where the 0.005 comes into play. So one thing that you have to take to the bank in these problems here is you need to be very careful about the wording here. Again, this is kind of like one of those times, once again, wording means a lot here, about what percentages go with which. So read the problems carefully so that way you go over the correct, again, the correct numbers that go with the correct designation. 0.995% a negative test, 0.005 a positive test. Okay, so let's look at letter A. Letter A states, what is the probability that the test comes back negative for all 5 people? So there's 5 randomly selected people, all right? And what happens if that test is, if they're all negative? So all 5 people are negative. Okay, let's take a look. So if all 5 are negative, what do you think we should do here? What do you think we should do in order to solve for this particular probability? What do you think could happen for this? Be the answer to this one here. The probability that all 5 people tested negative for this test here. Convert to fraction. Not in this case here. No, I like that, Mazdy. That's correct. 0.995 to the 5th power. That's right. We don't really want to convert to a fraction here. We're just going to get our decimals here. But let's think of it this way. Remember that each person here is independent, right? You're not selecting 2 people from the same household per se. You are selecting random people from random households. Okay, so it could be literally anywhere. Again, if you need to, draw your boxes. All right, so the first person, second person, third person, fourth person, and the 5th person. Okay, and we want to take a look at the probability that they tested negative. So the first person that tested negative, that's a 0.995% chance. Second person, 0.995. Third, 0.995. Fourth, 0.995. And last, once again, a 0.995. So again, they all tested negative, and this is the probability that they would test negative according to the test. So this would net 0.995 to the 5th power. Anybody have an answer for me here, by the way? That to the 5th power. .995 to the 5th power. I can wait, guys. It's fine. 4.975? I'm not multiplying by 5, my friend. 0.9752, okay. That's correct, yes. Good. Yeah, well, I was going to say, you have a 497.5% chance. Holy moly. I'd be like, wow, that's a pretty good odds you got there. 497.5% chance. Okay, good. So 0.9752 will go out to 4 decimal places here as normal. Okay. Okay, so that's letter A. That one isn't too bad. Now, let's get to the other part of this question here. All right. Let's look at letter B. All right. So letter B states, what is the probability that the test comes back positive for at least one of the 5 people? All right. So the probability that the test is at least one positive. So we're assuming, so at least one positive out of the 5. So we still have the same 5 people that we tested over. Fine. But now we're testing if at least one of those 5 tested positive. Okay. Well, what does at least one mean? Can anybody tell me what's another way to state the words at least one? This is one of those things that is pretty important here. Yes, one or more is correct. Okay. So we can look at it this way. We says, okay, if you have at least one, this is the probability of one or more. Now remember, there are a lot of different cases here for one or more, right? What cases do we have here? We have, again, I have the probability of one person testing positive. I have 2 people testing positive. I have 3 people testing positive. I have 4 people testing positive. Or heck, I have all 5 people testing positive. Those are entirely plausible scenarios, right? That's what it would mean to be one or more. So I would have, say, I could do the probability of 1 plus the probability of 2 positives, plus the probability of 3 positives, plus the probability of 4 positives, plus the probability of all 5 positives. So we can look at it that way, and that's perfectly fine. You know, that's entirely plausible. I think that's okay. I do have a problem though. Okay. There is one problem to this. So let's talk about said problem. Here's the problem with this scenario. This is a perfectly valid way to actually compute the probability. You can add each one of those cases together, and we are indeed going to get our final answer. Okay, no question about it. The problem with this is that this is going to take a long time to do. Okay, so let's be honest with ourselves here. This by itself, you have 5 different cases, you have 5 different probabilities to find, and then you have to add it together at the end, all at the same, all at the end of the day. That's a pretty long process and a lot of work. All right. So maybe, just maybe, we don't really look at it this way, although this is technically absolutely correct. So let's talk about the key about how we can handle at least in a different manner. Okay. So the key here of what we're going to do is instead of adding 5 individual cases, okay, adding 5 individual cases sounds pretty rough. I don't really want to do that. I don't want to add 1, 2, 3, 4, and 5 for all those probabilities. That's a pain. What we can do is we can use the rule of complements. So this is something that we talked about on Monday, is we did talk about the rule of complements. So let's think of it this way. Using the rule of complements, remember complements means the word kind of not, right? So I can use the probability of 1 or more, 1 or more positive, is equal to 1 minus, well, what is the opposite here of 1 or more positives? What's the opposite of 1 or more positives here? What do you guys think? What is the opposite of 1 or more positives? One or less? Well, I can't really say, I can't, okay, so here's the problem. Remember when we say one or more, okay? When we say one or more includes one. So if we're looking at the opposite, we don't want to include one. That's why I can't say one or less, because that would include one. I can't include one. So got to take that away. It's so it can't be one or less. One or more negative. Fortunately, that's not quite true here in this case. I can see where you're coming from there, Natty, but not quite. It's okay. So less than one. Okay. That is correct, Beth. There is less than one. How can I rephrase less than one in this context, Beth? Well, I like where you're going with this. It has to be less than one, I agree. How can I rephrase less than one? None, right? Because what cases do we have here? Okay, I don't have negative cases. I can't have negative people. All right, so I have a zero cases, one case, two case, three case, four case, and five case. Okay, I have all five of those cases. I have all six of those cases, pardon me. 0, 1, 2, 3, 4, and 5. So I would say, all right, the opposite of the probability of one or more positives is going to be 0 positive. Okay, so they're all negative, or again, you could say all negative. Whichever way you want to call it, they mean the same thing. Right. So what we're doing is we're just kind of shifting our perspective to the opposite, and how we define the opposite is basically removing everything. We're removing all of the, we want to have 1, 2, 3, 4, and 5, but we're just removing the one case that's also there. We're removing the 0 case that's also exists in this in these problems here. So again, we have 0, we have 1. So this is essentially what we're doing here. Or 5. So all we're doing here is just taking away this first case by doing 1 minus, and then everything else is going to be take care of all the rest of these cases after we do the law of complement, the rule of complements. Okay, that's all we're doing here in this instance. If we're to look at it from a picture perspective, that's what it looks like. Are there any questions about that? I want to make it crystal clear that it's confusing at first because of this fact, but it makes solving the problem that much easier. So you only have to take away one case to get all the 5 other cases, instead of adding up all the 5 cases instead. Are there any questions about that? I want to be sure. I think that's fair. I want to be sure everybody's on the same page here, so be sure that if there are any other questions. Okay. All right. That's fine. Yeah, it does require a little bit more practice, that's true. I just want to be sure that on this particular point that you guys are, you guys know what's going on. Now here's the question here. Let's do the actual numbers part. What's the probability that we have 0 positives or all negatives? What's that probability? What's that probability going to be? Probability that they're all negative. What's that exact value? Probability that you have 0 positives or all of them being negative. either way you want to call it. Anybody can tell me? What's that probability? You're back to stay? Okay, very good. Welcome back. 0.9752, that is correct. Yes. So if you recall, we found 0.9752 in the last part of this problem here in part A. That was the probability that all 5 were negative, right? So we're going to use our previous part and we're going to use it directly into part B, and we can find out. Oh, well, have a very nice day, French toast. Have a very nice day. I hope you have a wonderful night. Thanks, my friend. So we have 1 minus 0.9752, and so we just if we just go ahead and do that out, we get 0.028. Okay. So we got again, we can use our previous result in part A, and we can directly find part B, which is just again the opposite here. All right. Any questions about that? Nope. Okay. I haven't. Let me think about that. So no. So I've been thinking about something here for this class, and I haven't done it with you guys for this class yet. But I want to ask. I want to ask you guys a question here, so I'm going to put up a poll here. Okay, so the question I'm going to put up here is, would you like to do Discord here? So Discord here will be like it's a, you can talk over it. Some people know Discord, but some people don't. Discord is like an app. You can actually talk over it like a voice app service. It's free. You can put it on your phone. You can put it on your PC. So if you want to ask me direct questions over voice chat, you can go ahead and do so there. I don't know about what everybody's opinion is, but I have a Discord already set up, so it's a matter of if you want to do Discord or not. Go ahead and mark that in the voting box up above. All right, if you would like to do Discord there, either yes or no. So, and Discord, what does Discord kind of look like here? My Discord page kind of looks like my Discord kind of looks like this. Okay, so this is what Discord looks like. You guys can ask me questions. You guys can talk to me about stuff. Yeah. So I mean, again, it's a free app, so if you need to talk to me over voice stuff there, then that's fine. There you go. I'll just wait for everybody's opinion on the topic. Okay, great. So here's what we'll do here. I know some of you said no, that's perfectly fine. Okay. not forcing you to get Discord if you don't want to. But there's an invite to Discord here. You can download Discord on your phone or on your PC. There's a Discord invite right here. Okay. So if you want to join my channel here on Discord, you can go ahead and do so. And then if you don't already have Discord, then you can just get it. It's pretty simple. But yeah, you'll pop up over here to the right hand side if you just click on the link there to my Discord page. Hey. So for those of you who want to do that, let's take a minute, and then you guys can set that up really quick, and then we'll get to the next problems here. So just set that up really super fast. It'll just take a minute for you. If it'll take a minute for you guys, so just do that, and then we'll get to the next problem. All right, I see a couple people already in. That's good. All right, so got a couple in there. Okay. Again, if you want to add yourself there, let me put the invite there. There we go. A squared plus b squared equals c squared. This is true. The Pythagorean theorem is true, okay? Absolutely 100% ninja. I ain't gonna lie. uh, all right. I'm doing good, my friend. How are you? Doing good. Just setting up some Discord stuff. Setting up some Discord stuff. Oh, a lot of people populating. That's good. So if you want, no, you're in. Very good. If you want, you can go ahead and let me go ahead and showcase this off here. Join this indeed is. So if you want here for Discord, you can go ahead and click on the math icon here, if on the left, and you'll join the math channel here. Okay. If you're on a phone, then you could just swipe right, and then you can just join the channel. So, okay. All right, there you go. If you just click on math on the left there, like Ujwal has done, then you can join the same channel that I'm on right now. All you have to do is just you can mute yourself there. Yeah, that'll be good. So the audio is a little out of sync between Discord and Twitch. So but there'll be times where you could just mute Twitch and then you could just talk on Discord. So Yeah, so if you see over there on the left, you see this math thing, just go ahead and click on that, and then you'll be in the chat. There you go. There you go. Nice job, Natty. All right. So I'll have you guys kind of make your way over here if you'd like. I'll mute myself for right now so you can listen to the stream. But yes, just in case. All right. Let's have I'll talk with you guys here if I'll talk to you in stream here. So in just a second. Give me just a second. Okay. So let me go to the example problems here. Okay. So I do want to do 2 examples here. I would like you guys to try 2 examples here. So the examples I would like you to try is to try numbers 18 and 24. So try number 18 first here, 18 and 24. So I'm going to put it up here on the screen. Numbers 18 and 24. So 18 is the life expectancy problem here, and 24 is the cold streaks problem here. Okay, so try number 24. You don't have to do part D, but you can try parts A, B, and C there. All right, so let's try that. And for those of you who want to just ask me questions directly, I'll be here on Discord, and you can ask me stuff. So that's perfectly fine. Right. So we're going to take a couple minutes and give this a try. All right, let's see if we have some questions here. I see Natty in there. Let's ask Natty. Hello? Hello? Natty, can you hear me? You can unmute your mic there.
Yeah, I could hear you. I was getting confused with the whole Twitch stream and then, yeah. But yeah, I'm
Okay,
confused.
okay. About the Twitch stream or about the
Oh,
problem?
the problem in general.
Oh,
Yeah.
okay. Yeah, for Twitch, you just have to go ahead and just mute it, and then you can listen to me here on Discord.
Okay.
So it can it kind of goes both ways. All right, so let's answer your question here. Which
Okay.
part are we confused
Okay, now
about
I'm
for
just
18?
like confused about the whole thing actually. Like I get it when you explain it, but then I don't get it when I do it by myself. So
That's okay. Did you try number 18 already?
I'm trying to like do it, but I don't know what I'm doing.
Okay, well, let's take a look at that here. It says, all right, so the probability that a randomly selected 40-year-old female will live to 41 is 0.99855.
Mm-hmm.
So it says, what's the probability that 2 randomly selected 40-year-old females will live to 41? Okay, so again, just draw a picture, okay?
Okay.
So I just, all I want you to do is just take it simple and then just draw a picture, okay? So drawing a picture, just Just trying to put this on half and half. That's not half. Computer, do my thing. All right. Okay, so all I would like you to do is just draw two lines, right?
Okay,
Here's the first person, and here's the second person. So the first person lived, right? So the
Right.
first person lives, and the second person lives, right?
Mm-hmm.
So each one is an independent person, right?
Right. So
what's the probability that the first person lives according to the problem? What's that probability?
So is that where you put that number 0.99855 on top?
That's right.
Okay.
That's okay. And what's the probability that the second person lives?
The same thing, right?
That's right.
Okay.
And that's all you're doing for that problem.
Oh, okay.
Now you're multiplying those two together, and there you go. You will get a probability that two people will live in that regard.
Okay. Oh, I was overthinking again. Okay.
That's okay.
So, we're not like squaring, it's just like direct multiplying it, right?
Mm-hmm.
So the answer is 0.9970.
Go to four.
Oh.
Go to 4 decimal places.
Okay, 0.9970.
7. What comes after 0?
Another 0.
Really?
Wait.
Sure.
Did I do something wrong?
Let me check something here. 99855.
Oh.
You should have 9971. You should have 99855 for both.
Oh. Okay.
Yeah, just be careful about that because on the homework problems, it's very particular how it wants things entered. So.
Okay. Cool.
All right. Why don't you give part B a try, okay?
Okay. Thank you.
You're welcome. Ujwal, are you there? Ujwal, you can unmute and undeafen yourself. I'm not sure why. Maybe Ujwal is there. But you can't hear me. I don't know. Oh, you're here? You can undeafen yourself and unmute yourself on Discord there. If you want, if you have your your mom's too loud.
I'm dead.
I don't know what to tell you, Ujwal. I don't know what to tell you there, buddy. Okay. I mean, I don't know why your mom's. All right. Does anybody else here on Discord or on chat here? Do you have any questions? Again, I just showed off the first part there. That was part A. So hopefully that gave you a little bit of inspiration about how to do the other parts here as well. So try parts B and C here as well for number 18, as well as number 24 here. I'm gonna put this back up, the big thing here. Again, pop over to Discord if you want to ask me a question in person there. Actually, bye. Something. All right. Just waiting for you guys here. It's weird why you're asking me stuff. Okay, so let's go ahead and do letter B here. Can you guys give me an answer here for letter B? What is the answer for letter B here? What is the probability that 5 randomly selected 40-year-old females will live to be 41? So probably they have 5 people will be randomly selected to live to 41. What did you guys get for that one? Hmm. 0.9925? 4.9928 doesn't make any sense. That would be a 499.28% chance. So that part there can't make much sense, unfortunately. Okay. 9928 is what Natty got there. Okay. Well, let's yeah, remember you can't multiply by 5. You're not multiplying by 5. If you get an answer that's above 1, you know that that you did that calculation wrong. So you have 5 people here. So you have again, you have 0.99855 and you have that all the way down. So this is going to equal 0.99855. Yeah, be careful about that. To the 5th power is what you're going to get here for that. And if you do that there, yeah, just be careful about that, yeah. We're going to get 0.9928 is correct. So Natty got that right. 9928 is the correct answer for that. Good. Okay. Questions about that? Nope. Okay. Oh, okay. Okay, that's what was happening here. Okay, okay. All right. Well, let's see if we can get the next one here then. Okay, so last part here for number 18, and then we'll look at a couple parts there for number 24. What's the probability that at least one of the randomly 5 selected 40-year-old females will not live to 41? So unfortunately, probability of at least one not living. Out of 5. So I should say out of 5. All right. Agreed. 0.0072. How do we get that? Yes, queen indeed. How do we get that? Yes, that is correct. Very, very good. Excellent. It's 1 minus the probability that all 5 live. Correct. So we're going to use just that last one there, 1 minus 0.9928, and that is correct here. Get 0.0072. All right, good beans. Nice job, nice job. Okay. Let's take a good look here at number 24 here really quick. I'm going to look at one of these, actually two of these parts here. Okay, so I want to look at let's look at letter C here. Find the probability that the hitter makes 5 consecutive outs and then reaches base safely. All right, so I'm going to, because I want to spend a little time on the next section here, so just kind of going to bound around here for just a second. All right, so basically, the hitter here in baseball, they basically will fail 70% of the time, and they'll succeed 30% of the time. So fail is 70%, and succeed is 30%. In this case here, what we talk about is that, okay, they make 5 consecutive outs or 5 consecutive failures, okay? And then the last one here is a success, okay? Actually, I'll put that in a different color. So success for the last one. So in this case here, we have a 70% failure rate, so 0.7. So the first 5 were failures, and then finally the last one was a success. We have a 30% chance of success. So if you want to figure out here, we actually have 6 at-bats here in this problem, and we're just going to multiply these values here together on the calculator in order to get that done. And so if we do this out here, 0.0504. Okay. So I want to highlight that last problem there really quick about how to go ahead and find, say, the probability here in this instance. By the way, really quick question here. Is this unusual? Would this be unusual to have 5 consecutive outs followed by a hit? Would this be unusual? Just barely no. Well, what was our threshold for unusual? This is true, Mazdi, I agree. What was our threshold for unusual again? 0.05, that's right. So 5% or 0.05, right? That's our threshold there. So it has to be below 5%, right? So below 5%, so below 0.05, or 5% is considered unusual. So if, again, you may see those questions pop up from time to time. We did talk about it before, way back when. It's now going to appear once again here when we talk about probabilities. So just be sure that you're aware about that fact. And again, if you do see those on some of the homework problems, you'll know exactly what it's talking about. All right. I would normally take a break here, but I need to do the next section here. Is it okay with you guys that we forego our break here, even though I know you guys, again, is it okay if we forego the break? Yes. Okay. Just want to be sure. All right. Thank you very much, everybody. Ask permission first, and then you know. All right. Okay. Let's do the next section then. All right. So go ahead and do this out here. Okay. So we're going to do the rest of the problems here on the handout for section 5.4. So let's go ahead and take a look at what we're doing here in this section here for the latter part of class. All right, so what we're going to be talking about here is we're going to be talking about conditional probabilities and computing probabilities using the general multiplication rule. Okay, so first of all, let's talk about what conditional probabilities are. So conditional probabilities, the definition of a conditional probability is the probability of one event B given that an event A has occurred. So we have a condition, we'll call that condition event A, and we want to find the probability of another event, event B, with that given condition already enforced or in place. Okay, so we're going to have two different events going on here. One will be the probability we need to find, and one will be the condition placed upon that probability. Now, for the notation here specifically, what does the notation look like here? Notation looks like P, probability here of B, again, given, and given here is this kind of, again, straight line going down. All right, so that kind of separator. B given A. So as you can see here on the right, we read it from left to right here. We say the probability of B given A. All right, so again, A will be our condition, and the probability of B with that condition is what we're trying to find. One of the biggest keys here into talking about how we can find conditional probability is if we read the probability left to right. Order is going to matter here for these probabilities, okay? And you'll see exactly how that works here in this instance when we look at a question. Okay, so let's take a good look here at question number 4. How do we compute conditional probability? Now, this is the, again, one of the things that I talked about here before is with conditional probability, we want to talk about specifically, what do we want to talk about? We want to talk about, of course, how you would approach that from two different angles. Here we have the probability of B given A is the probability of A and B divided by the probability of A, or the number of A and B divided by the number of A. Okay, so we can look at it from two different perspectives here, either using probabilities or the number in each event or category. All right. Now, as I stated before here, order matters. Now, why does order matter here when it comes to conditional probability? It's because this fact is also true. The probability of B given A is not the same as the probability of A given B. The probability of B given A is not the same as the probability of A given B. Remember, order matters here. Remember, this first one here has our condition of A, and then we have to find the probability of B with that condition of A. However, in the other one, we have a condition of B, remember given B, so we have a condition of B, and we're trying to find the probability of A with that condition. So we're going to have two different values here in these cases, and we'll also look at examples. We'll also look at an example about where that actually fits in. Okay, so let's take a good look at an example here. Yeah, let's look at an example. So let's look at an example here. Let's do that right now. And let's see how we can tackle some of these problems here. All right. All right. All right. So let's take a good gander here at number 17. Okay, so if you recall back in chapter 4, we looked at contingency tables. Okay. Now, when we looked at contingency tables, remember they had columns and they had rows with those contingency tables. You probably will see, if you haven't done the test yet already, you will see contingency tables appear on the test as well. All right. But in any case, all right, what we're going to use is we're going to now use this contingency table here, like we see in number 17, all right, and we can figure out probabilities based on that contingency table, just like we did from before. Okay, but just in a slightly different light here. So let's go ahead and read this off here. This is pretty much the same question we looked at in chapter 4. Again, it's a Harris poll here, and random sample said, when you see an ad emphasizing a product's made in America, are you more likely to buy it, less likely to buy it, or neither more or less or nor less likely to buy it? Okay, again, and then here we have the results of the survey. There it is. Now, Let's take a look at the probabilities here. It is on the next page, so I'll just read them off, and we'll take a look at it. Okay. So what is the probability that a randomly selected individual is 35 to 44 years of age, given that the individual is more likely to buy a product emphasized as made in America? So here we're given the probability of 35 to 44, given that we're more likely to buy this product. Okay, so I'm going to guide you through this problem on my own here first, and then you'll see exactly how we're just going to put these given probabilities together. Now, there's going to be two parts to this, as you saw in the formula. In the formula, we had a numerator and denominator here. So some numbers got to go up top, and some numbers got to go on the bottom. So where do I start? Well, the first thing that I do is I start here with my given condition. So this is my given condition. So with conditional probabilities, you're now going to be working in a much more smaller, more narrower box than maybe what we're doing from before. So before we could look at, say, the full 2160. We're not doing that here for conditional probabilities because we're restricted by a very specific condition, or again, a very specific rule. We're given the fact that we have more likely in this case. Well, I always start at the denominator first. Okay, so starting at the denominator first, I see how many people are in my given condition. Well, how many people are more likely according to my table? Well, I have 1,329 people who are more likely according to my table here. So we're just looking at this here specifically. We have 1,329. Okay, I'm just looking at this row here. Okay, just the more likely row. So this is all I'm looking at here, just this row that I've highlighted here. All right. Now I have to ask myself, okay, out of those 1,329 people, how many people are in the 35 to 44 category? Because I'm trying to find that probability. Well, out of those 1,329 people, 329 are in the 35 to 44 category. That's correct. That's right. So here I've now established my fraction, which should get me to my final decimal result here for our final answer. So we have 329 divided by 1329, and so we get 0.2476. Okay. Put that on the next slide, actually. All right, good. Are there any questions about that example there? Any questions at all? Nope. Okay. Okay. Now, there is something important that I do want to point out here to you guys, okay? And this is actually a very common mistake I see in these problems. So this is kind of like your orange warning sign here for these problems, okay? Oftentimes in these problems, I see a lot of people mixing up the numbers here, okay? Meaning to say they may sometimes put 1329 on top and 329 on the bottom. So again, just like we did last time here, make sure you get a probability. Get the probability. Make sure you get a probability between 0 and 1. As we've already seen here today, we don't want probabilities that are bigger than 1. Okay, obviously that won't make any sense. If you get negative probabilities, well, that clearly doesn't make sense. So, yeah, just be sure that you don't put the numbers in the wrong places. But I always start from the denominator, and then I put a number in the numerator. And that number, if I divide those two numbers together, needs to be between 0 and 1. Okay, it has to reflect a percentage in decimal, a proper percentage in decimal. Okay, so a common mistake I see in these problems here, so I want to make you aware about that fact. All right, let's do the second part here. Let's do letter B. Letter B is basically reversing stuff around. What happens if I take the probability of more likely given 35 to 44? So probability of more likely given 35 to 44. So let's put it together here. All right. So let's look at the table here, everybody, and then you guys can answer for me here. Let's look at the denominator here. Let's look at our given condition, 35 to 44. How many people are in the 35 to 44 category? How many people are in the 35 to 44 category according to our table? $536. Okay, that's correct, right? So if we look at our table here, on our category of 35 to 44, 536 happen to be in that category. Now we look at the second half. Out of the 536 of people between 35 to 44, how many of them said more likely? How many people are more likely in the 35 to 44 category? Okay, that's right. 329. That's correct. Nice, nice. So now you can see we have a different probability. Similar numbers, okay, but very different probability. So in this case here, we get 6, 1, 3, 8. Okay. So you see how the probabilities from one way, not the same going the other way. Okay. All right, any questions about that example there? Any questions at all? All right, let's have you guys try one now. I want you guys to get comfortable with this idea. I'm going to throw one your way. I want to be sure that you guys at least get this part down here. All right, what's the probability of neither given 55 plus? So can anybody tell me what would be the probability of neither according to our table in number 17? Probability of neither given 55 plus. Okay. Take a look at some other answers here. All right, so we have Mazdia, Joel, and Beth coming in with some answers here. Anybody else? chime in with any other answers. Okay, Susan's got that. That's fine. All right, let's take a good look here. Want to look at 55 plus first and foremost. So how many people in 55 plus? We have 536 people in 55 plus. How many of those people in the 55 plus category are underneath neither? Well, 118 of them. That is correct. So 118 out of 536 is spot on. And let's see if we indeed get that answer you guys have stated here. It should be the case, and it is. Okay, so 0.2201 is absolutely correct. Very nice job. All right, good. Very good. Took it in nice, simple steps. All right, good job. Good job. A little more practice, and I know you'll get that down. That one isn't too bad. You just have to kind of look at a couple things. Okay. Okay. I gotta do, actually. I don't know if I'll have time to do that. So I had something planned, but I'm gonna have to skip that and on to the next part. So, humbug. All right. Let's look at number 5. All right. So number 5 says, what is the general multiplication rule? Okay, so the general multiplication rule is just basically an extension off of the last question, which was just the conditional probability. All you need to do is multiply by the probability of A on both sides, and you get the multiplication rule here. Probability of A and B is equivalent to the probability of A times the probability of B given A. Now, although this rule exists, the more along the lines of we're going to use the general addition rule, general multiplication rule, pardon me. We're going to use this more in a brute force kind of method. Okay, and where do we use this in a brute force kind of method to apply this particular formula? Well, we use it in two very particular instances. That is sampling with replacement and sampling without replacement. So the last question here on this handout is, what can we say about sampling with and without replacement? So with replacement is, again, they're both fairly simple concepts, but it does actually change how you actually have to approach finding the said probabilities. So let's take a look at both of them. With replacement, that means that we replace the item back, i.e. we have the same number of items for each pull. So if we say have a deck of 52 cards, okay, and we pull out a card. Now, if we pull out a card, whatever that card is, it doesn't matter. Maybe it's a magician saying, hey, take a card, any card. Pull out a card, you say, okay, hey, it's whatever. And they ask you put it back in the deck. So you replace the card back, okay? So that's replacement. So there's still 52 cards in the deck when you hand it back. All right, seems fair. Without replacement is exactly the opposite here. Again, you pull the card out of the deck. Magician says, okay, you hold on to the card or put it aside. You take that card out, you put it aside, and now there's 51 cards left in the deck. Maybe you take out another card, put that card aside. Now there's 50 cards left in the deck. You're not replacing it at the end of the day. Once again, with replacement and without replacement, incredibly important because we have to watch out for keywords such as at least and exactly. Okay, there's two different ways to actually approach probabilities with the words at least and exactly, and of course with replacement and without replacement. We have to be a little bit extra careful about how we do that. Okay, let's take a look at an example here, and let's see exactly how we can solve some of these problems. I'm going to look at a specific question here. So the specific question here in tandem is going to be number 27. Okay, so let's look at 27 here. We'll read it off, and we'll take a look at how we can solve for these probabilities. It's not hard. It's just again, we just have to be sure that our perspective is correct. All right. So playing music on a random setting. So suppose that a digital music player has 13 tracks. After listening to all the songs, you decide that you like 5 of them. With the random feature on your player, each of the 13 songs is played once in random order. Find the probability that among the first 2 songs played, being at letter A here, you like both of them. Okay. Now we need to break this down very, very carefully. Let's do that here in this problem. First of all, we have 13 tracks on this digital music player. All right, we like 5 of them. 5 we like, right? How about the others? How many do we not like? How many disliked songs do we have? Okay, we have 8, right? We don't like 8 of them. So 8 songs is a dislike. All right, and this will prove to be important in just a second. Okay, so one of the other things to keep in mind here is that if you take a look here, it says each of the 13 songs is played once in random order. So let's say we play a song here, and once that song is played, that song won't come back into the order until all the other songs have been played. Okay? So what that means here in this case is that in this problem here, we're going to be dealing with something without replacement. Okay? So although it's random, it is truly random in terms of the song that it picks first, second, third. It has to go through all 13 songs first and then loop back around to whatever afterward. So we're not dealing with replacement here. Now, we have to pick in the first 2 songs here according to the problem. We like both songs. Let's look at part A. Probably that we like both. So again, let's draw a picture here. Okay, let's draw a picture. First song we like. Second song we like. So I'll put an L for like here. Now, we play the first song here. What's the probability here? What's the odds that we get a song that we like for the first song? What do you guys think? The probability that we get a song that we like here. 1 out of 13. Not quite. Remember, how many songs do we like here, Ujwal? Yeah, 5 out of 13, right? So we get 5 out of 13 songs are songs that we like. Okay, so that has to happen here. First song that comes up, it's a song we like. So we have a 5 out of 13 chance where that happens. Agreed. Okay, now we're not going to round right here just yet. Leave it as a fraction for right now. We'll round it afterwards. So, again, this is probably one of those things that I will stress here. Don't round in the middle, round in the end. Okay. So when you get to the end of the problem, then go ahead and round to your 4 decimal places, but not in the middle of the process. So leave it as 5 over 13, and once you go ahead and multiply, divide, do whatever it is that you have to do, then go ahead and do that. So I'll say that. Okay, cool. Yeah, just making sure you guys are careful because again, like because you and Beth had said, yeah, 0.3846, which is correct for 5 out of 13, but I don't want you to do it in the middle because even if you do like the homework problems, it's going to mark you wrong because you rounded in the middle and then you're off by like 1 or 2 decimal places. Get frustrated. So you obviously don't want that to happen. How about the second song? So now the first song is over. Now the second song plays, and it's another song that you like. What are the odds that you get another song that you like? 4 out of 12. Yes, that is correct. Very good. Right? So now there is one less song in the queue. Okay. You started off with 5 songs you like. Now you take off one. You have 4 songs left that are like in the pool. But then you also knocked off 1 song in the pool overall. So you have 4 songs that you like out of 12 possibilities. So 4 out of 12. Now we can go ahead and multiply these together, and now we can go ahead and see what we got. So here we get 0.1282 as our final answer here for our problem. Okay, stuff. So far, so good. All right. Let's go with the next one here. How about dislike both? So let's say we dislike both here. We'll put D here for dislike. So let's take a good look here at both of these guys. So how about the first song here? What is the odds that we don't like the first song in this question? Eight out of 13. Yeah, that's right. 8 out of 13 is correct. Good, good, good. How about the second song? What are the odds that we do not like the second song either? Okay, 7 out of 12. Very good. That is correct. We could go ahead and multiply these together. Wonderful, wonderful, wonderful. Does anybody have an answer for me here? We'll go to 4 decimal places as usual. So 3590. Okay, good. Perfect. Alrighty. So far, so good. Okay. Let's take a look at the third one here. So here. Actually, so let's go to the third one here. So the probability that we like exactly one of them. What's the probability that we like exactly one? So the probability of liking exactly one. Now this problem here is a bit tricky, okay? Because we actually, in this case here, let's think of I'm going to showcase the reasoning here. The reasoning behind this problem is that we have 2 cases of liking exactly one. The first case that we could end up saying is that let's say we play the tracks. The first track that comes up is a song that we like. But then the second one here is a song that we dislike. Or it could be vice versa, where the first song is going to be a song we dislike, but the second song is a song we like. Both of these cases reflect exactly one song that we like here. So we're going to add, that's why you see the addition there in the middle. We're going to add those 2 probabilities together since both reflect exactly one song that we like. Okay? So if we go through carefully for each case, then we're going to be able to find what our final answer is going to be. let's look at each one. Okay, let's say the first song we like here. Now, we've already established this one here. That was 5 out of 13. 5 out of 13 chance the first track I'm gonna like. Now, let's say the second song plays, but now it's a song we dislike. What are the odds in that case that the second song we play is a song we dislike after the first song was a song we like? 8 out of 12. Okay, that is correct. Good. All right, great. That's correct. Let's take care of the other case, and then we can add these two together. So we know that the odds of getting a dislike from the previous part here, is 8 out of 13. How about the second track? Let's say the second track plays, and it's a song we like. What are the odds that we get a song that we like here in the second one? Okay, right? So we got our first song here is a song we disliked, but our second song is a song we liked here. So we have 5 songs that we like out of 12 possible songs that were left over. Okay, good. That's right. Be a little careful about that. Remember, didn't take away any songs that we liked because the first song was a song we disliked. So that's why it can't be 4 out of 12. That's why it'll be 5 out of 12. Yeah, so these are 2 separate cases. Okay, these are 2 separate cases. Like and dislike, dislike and like, these are 2 separate things, 2 independent things. So we're separating them from each other. Anybody have an answer for me here if we add these together? So if we add these together, what do we get? What's our answer for this? Uh-oh. 2.0833. Oh no. How did we get something so large? Oh no. 0.5128. I would agree with that part. That part's true. Not sure how you got an answer that big. You make sure you put parentheses around those fractions just in case. All right. Yeah, remember, Susan. Remember, anytime you get above a 1, do the work again. Just do the work again. Don't even question it. Just do the work again. Negative value, do the negative probability, do the work again. Okay, so that's without replacement. Now there is the other side of the coin here for these type of problems here, and that is if you did it with replacement there. Oh, you added them all together. Oh yeah, yeah. Oh okay, that's what happened. Yeah, you have to multiply these together, and then add those 2 values together afterward. Oh, no wonder. I was like, oh, okay. Okay, so what happens if we go with replacement? So with replacement here, if it was with replacement here, for example, with replacement here is significantly easier. So if we were to do all three probabilities again with replacement, let's say we had a song we like and another song that we like, well, it's actually fairly easy because you're just putting the same, you're having true randomness, right? You could play one song and then that song could pop up again for whatever reason. So that's going to be, say, 5 out of 13 here for the first song. And then once again, if for the second song, it's going to be the same exact odds, a 5 out of 13 chance, since you're putting the same song back into the pool and it could, pop up again as the second song. So it'd be 5 out of 13 times 5 out of 13. If you had disliked both songs, like in part B, well, then it would be 8 out of 13 and 8 out of 13. Again, the numbers don't change here. They're exactly the same. In part C, it would be, again, it'd be a like and dislike here. You'd have a like and dislike here, for example. So that'd be 5 out of 13. And the one big change here is that this would be, instead of 8 out of 12, this would be 8 out of 13. Again, the number of songs don't change because you're replacing that song back into the pool of songs anyway. And then you repeat the process here again. Really, nothing much changes. You get 8 out of 13 and you get 5 out of 13. So, okay, so if you want to look at it with replacement, it's significantly easier because you're just literally putting it back in and the odds aren't really changing whatsoever. So, and then you could figure those out doing the calculator stuff. Okay, any questions about section 5.4? Any questions about section 5.4? All right. So just to let you know here, in the future, there may be times I may ask you for a little bit of group work here on Discord. So I've just wanted to set everybody up for Discord here. For the people who do want to participate in that little group work there, you have a chance to ask me questions directly in the middle of class about, as you can tell, certain topics and whatnot. So again, feel free to do so when we get to do a little bit of group work here. There'll be a few times we're going to be doing some group work here, especially with finding some probabilities. Doing in groups will be actually rather helpful because some processes can be a little confusing. All right, but doing it together with other people can't be a bad thing. All right. Okay. Well, straight shot here today. I do apologize. I'm sure that your brains are shish kebab fried. So I do want to thank you guys for coming on out here today to the stream. All right. Thank you so very much. You guys are absolutely 1000% wonderful people. Okay. There we go. Switch this here. I love all of you guys. All of you guys are wonderful and great. Okay. Thank you so much for coming on out. And yeah. Everybody, have yourself a wonderful night. All right. Take care of yourself. Have a great weekend. And remember, stay safe, stay healthy, and most importantly, everybody, stay sane. All right. We will see you again on Monday. All right. Take care. And again, contact me via email if you have any questions. All right. All right. Have a great one, everyone. And we will see you later. If you have questions as well, just ask. Okay, my friend? You know where I am at. Not going anywhere. All right. Try some problems out and see how it works. Okay. If it's still confusing, we got more than enough time to go over that stuff there. You can ask me questions. I'll be happy to help out. See you Monday, my camera. Thank you very much, camera. I really appreciate your time. Thank you so much. Very, very kind to meet you today. Very kind for you to come out. All right, everybody. Okay, very good. Remember, everybody, focus on the homework and stuff, okay? Remember that the homework and tests are due on Sunday, so be sure to finish that first. All right, make sure you get those priorities done. All right. Hey. Look, you make the time out for me, and I really appreciate that, camera. I really do. Thank you so much. All right, everybody. Thank you so much again. We will see you all next week. All right. Take care, everybody. Have a wonderful night. All right. See you, everybody. All right. Bye. Bye, everybody.